Hi there, in this video I want to talk about dividing rationals and rationalizing denominators. When we look at a fraction that has a radical in the denominator, we need to deal with that with a process that's called rationalizing the denominator. If a number is under a radical and can't be simplified, it's irrational. So radical 5 is irrational, radical 3 is irrational. So the process is called rationalizing the denominators because when we finish, there will no longer be any radicals in the denominator. When you multiply a fraction by a big fat 1, it doesn't change the answer. Well, what we're going to do is we're going to multiply by a big fat 1, but it's going to be in the form of radical 5 over radical 5. We're going to pick the buddy of this guy. So if I do that, then what happens is in the numerator, radical 2 times radical 5 gives me radical 10. In the denominator, radical 5 times radical 5, because they're buddies, I get 5. Now my answer is as simple as it can be right here. Don't cancel a number that's not under a radical with a number that is under a radical, no matter how tempting it is. Okay, let's look at this second problem. I have a radical 3 in the denominator, so I'm going to multiply both the top and bottom by radical 3 over radical 3 because that's really just a big fat 1. So when I do that, my answer turns out to be 8 radical 3 over 3. Okay, so here's a couple other examples. I'm going to multiply this fraction by radical 6 over radical 6. So top and bottom is a radical 6 because of the buddies. I want to be able to put the buddies together. So when I do that, I end up getting 4 radical 6, and then in the denominator I get 6. Well, you cannot cancel the 6 and the 6 because one's under the radical and one's not. But you can cancel 2 goes in here twice and 2 goes in here 3 times. So I can cancel the 2 and the 6, the 4 and the 6, and get 2 radical 6 over 3. And for this second one, if I multiply times radical 5 over radical 5, I'm going to get the 2, and then I multiply the radicals together and I get radical 15. And then these are buddies, so I just get 5. Okay, I'm going to show you 3 methods for rationalizing denominators, and you can pick whichever method works the best. The one that will always work is what I call the buddy method. So if you multiply and you choose the buddy, in this case it's radical 8, and you multiply by radical 8 over radical 8, it will always work. I get 3 radical 8 over 8. Now the problem with this is that radical 8 is not in its simplest form, so I need to go over here somewhere and do some cloud work, because the square root of 8 is really the square root of 4 times the square root of 2, so that's 2 times the square root of 2. So I can come back over here and I can take out the radical 8 and I can write what it equals, which is 2 radical 2. Now you can do one of two things. You can see that you can cancel the 2 and the 8 right away, or you can go ahead and multiply it and then do your canceling. Because I can say 2 goes in here 3 times, 2 goes in here 4 times, and so my final answer is 3 radical 2 over 4. Okay, the second method would be to take this radical 8 and simplify it right away. Now we already have this cloud work over here, so we know that radical 8 is really 2 radical 2. So this problem is really 3 over 2 radical 2. And if that's the case, Then I look at the radical 2 down here, and that's my buddy, so I'm going to multiply by radical 2 over radical 2. Now when I do that, the numerator gives me 3 radical 2, and the denominator, you got to be careful here, because if I put these two guys together, that gives me a 2, but I have another 2 here, so I've actually got 2 times 2, which is 4. And that's my final answer. And for the last one, if you look at radical 8, and remember our string of perfect squares? Our perfect squares, I'll just write them up here. Our perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so forth. If you can find a number to multiply 8 by to give you one of the perfect squares, that will also be a way to get rid of the radical in the denominator. So when I look at this, I know that 8 times 2 gives me 16. So what I'm going to do is I'm going to multiply by radical 2 over radical 2, because then that gives me a 3 radical 2 in the numerator and a radical 16 in the denominator. I chose it so that it would give me a perfect square, because then I could simplify that and get rid of the radical. So look at our answers. They're all the same. 3 radical 2 over 4. They're all the same. So you can use any of these 3 methods. If you want to remember just one thing, just pick the buddy. But then make sure you simplify any radicals and fractions as you finish the problem. The second one is to simplify the radical first and then choose the buddy. And the third one is to just look and see what kind of a perfect square you could get if you multiplied a different radical times your denominator. Okay, let's look at a couple examples. If I look at a radical 12 here, I could just multiply by radical 12 over radical 12. But I notice that if I take 12 times 3, that would give me 36, and that's one of my perfect squares. So I'm going to do that instead. I'm going to multiply by radical 3 over radical 3, because that will give me a perfect square. 8 times radical 5 times radical 3 gives me 8 radical 15, and then the denominator gives me radical 36, which I know to be 6. Now I've got one more step that needs to be done here, and that is to simplify. 2 goes in here 4 times, 2 goes in here 3 times, so my final answer is 4 radical 15 over 3. Okay, now this one on the bottom here is a little bit different, because if I look at 8 over 50, if that were a fraction, I could simplify that. So we have a rule for radicals that say when I have the division of 2 radicals, I can put them under the same radical. So if I do that, I can simplify that radical to 4 over 25. And the square root of 4 over 25, if I need to do this, I can put the numerator and the denominator back under their own radicals. I know the square root of 4 is 2, and I know the square root of 25 is 5. So if you see something that can be simplified, go ahead and put it together so you have a single fraction under the radical, simplify, split it apart again, and then carry on with whatever method you're going to use. Alright, let's take a look at other roots. This has a cubed root of 5 in the denominator. Now if you remember, if I want to multiply the cubed root of 5 times something to get rid of the radical, I need 3 buddies. So in order to deal with this fraction, I would need to multiply the cubed root of 5 over the cubed root of 5 and do it again. Because that way I get 3 buddies, and we know that when you have 3 buddies in cubed roots, they undo each other, and I just get 5. In the numerator, I've got 1 times the cubed root of 25. Don't be tempted to change this into a 5 because this is a cubed root of 25. We don't know what that is. So this is actually your final answer. All right, here's another example that's going to kind of correlate to what I said about square roots. I can automatically pick 2 more buddies, or if I can think and know my perfect cubes, which are, they get pretty large pretty fast, but I do know that 2 cubed is 8. So I could choose here, instead of doing the buddy thing, I could just multiply by the cubed root of 4 times the cubed root of 4. Because in the denominator, I get the cubed root of 8, which I know. In the numerator, I get 7 times the cubed root of 4. So my final answer would be 7 times the cubed root of 4 over 2. All right, let's look at this problem, because this one has an index of 4, and I've got a variable raised to an exponent underneath. Now, if I break that apart, that's the same as the fourth root of x to the fourth, fourth root of x to the fourth, fourth root of x to the first, because here's my 4, 4, and 1. Here's my 9 x's. Now, these guys will both turn into x's. This will turn into an x, and this will turn into an x. Because anytime the index and the root with the same exponent, they will undo each other. Now this guy needs 3 more x's to make it work. So I need to multiply by the fourth root of x cubed over the fourth root of x cubed. If I do that, in the numerator I get 2 times the fourth root of x cubed over, this gives me an x, and I've got an x here and an x here, so I end up with an x cubed. I want to show you an alternate way of looking at this that uses our knowledge of radicals and our knowledge of fractional exponents. If the denominator has an exponent under the radical that is a multiple of the index, then you can simplify it. So if I think about the multiples of 4, I've got 4, 8, 12, 16, 20, and so forth. This 9 falls right in between the 8 and the 12. So if I had 3 more x's, I would have an x to the 12th. So let's look what happens if I put the fourth root of x to the third top and bottom. Numerator is what we would expect, the fourth root of x to the third. In the denominator, though, I am going to put those two together, and I get the fourth root of x to the 12th. So remember what we did when we turned radicals into fractional exponents? This is really x to the 12 fourths. And x to the 12 fourths is just x to the third. So my final answer is the same as we had above, but it got there a little differently. So you can split it apart like this if you want to, or if you can make the exponent a multiple of the index, change it to a fractional exponent and then simplify it. Okay, let's look at one more example. If I have division of radicals, it's going to be a lot easier to manage if I look at it as a fraction. So I'm going to write it with the division bar. And then I think what would be the best thing to do would be to put them together under a single radical, because I can see that there's some simplifying I can do. Once I get it under a single fraction, I can cancel the 3's, because 3 goes into both of those once. This x will cancel one of these, and what's left is x to the third. So let's write down what we have left. We have got the square root of y cubed over the square root of x cubed. Now the x cubed needs to be rationalized, and the square root of y cubed needs to be simplified. So let's take care of the denominator first. I can make that an x to the fourth if I just multiply it by the square root of x to the first. If I do that, I get something in the denominator that I do know the square root of. We know the square roots of anything raised to an even power. And in the numerator, I can put these together. So let's carry it on down here. The denominator, the square root of x to the fourth, is x squared. In the numerator, I'm going to need to simplify that. So maybe I'll come over here and do a little bit of cloud work. If I've got the square root of xy cubed, I split them apart, give each its own radical. This guy, I need to break one off because it has an odd exponent. This gives me y. These all come down as they were. Okay, so when I look at all that together, I can come over here and write y radical xy, and then I need to look at it and see if there's anything else I can cancel. I can't cancel the x's because one's under a radical and one's not. So this actually would be my final answer. So just going back to this problem, just as a quick review, you can always pick the buddy of the denominator, and remember that what we really have is we are not changing the value of the fraction, we're just multiplying by 1 in some form. You can pick the buddy, you can simplify the radical first, or you can look for something that will multiply to give you a perfect square. It doesn't matter which one you want to do, but make sure that your final answer is always simplified as much as possible. If you have radicals with different indexes, just remember that the number of buddies you need matches the index. So if you're in cubed roots, you need 3 buddies, fourth roots, 4 buddies, and so forth. All right, there you go. Go do your homework.